Okay, here we have a series, n over n² plus 1. It goes from 1 to infinity. With this one, we want to use the integral test. Why do we want to use the integral test? Because it passes two criteria. One criteria is that it's monotonic decreasing. That means that it's always decreasing. The sequences, that is. The sequence is always decreasing. The series itself, because it consists of addition of terms that are always positive, is going to increase. But the sequence, n over n² plus 1, with each passing term, each term is going to be smaller and smaller and smaller because we're plugging in numbers from 1 to infinity, and that means that the denominator is going to get larger and larger and larger. When you have a larger and larger denominator, your entire value becomes smaller. So this does become smaller with each passing term of that sequence. That means that for the series, to find out if the series converges or diverges, we can use the integral test because it passes that one criterion and it passes the other criterion, which is that this is always, no matter what you plug in, it's always going to be not negative. So you plug in 1, you plug in 2, you plug in 3, all the way on to infinity. How could this ever be negative, right? So it passes those two criteria. It's never negative, and it's monotonic decrease. So we can use the integral test. What is the integral test? We just take the integral of that. So we have integral. We could change this to x's if you want. So we could have x over x² plus 1 dx, because we're just more used to x's, I guess, with doing integrals. So that's from 1 to infinity. But remember, we can't directly work with infinity with these integrals. I know it's been a long time since you're pretty far ahead if you're watching this. So we replace that with t. And we let the limit as t approaches infinity do the work of representing that idea. So now, how do we actually solve this? Well, we could do a u sub. When you do a u sub, you tend to have the more complex thing be u and what's in the denominator. So u equals x² plus 1, which means that the derivative is 2x dx. Okay, now we make our substitution back. We have from 1 to t. We replace this with u. The x is still there. Dx becomes du over 2x. We solved for dx, so that's what we have. Du over 2x. The x's cancel out, as you can see, so that goes away with that. We're left with a 1 over u. You could bring the 1/2 outside. 1/2 like this. And so what is this 1 over u? Well, that's just the natural log. When you take the integral of this, you get the integral goes away. You've evaluated that integral. When you evaluate, it's the natural log of the absolute value of u. That's just 1 over u. The integral of 1 over u is this, as we should know by now. And it's multiplied by 1/2, of course. The upper bound is t. The lower bound is 1. The way we evaluate this is by plugging in the upper bound and subtracting from the lower bound. But remember, we made a u sub, so we have to undo that u sub after we do our evaluation. So u is x² plus 1. x² plus 1 goes in there. So we take plugging in t, and we subtract plugging in 1 of this same formula. So we have 1/2 natural log of t² plus 1. And over here, we're plugging in 1 for that x, which gives us 2. 1 plus 1 is 2. So we're remember that we're bringing down the limit with each passing move that we make. Don't forget your limit, which is the start of the show here. Limit as t approaches infinity. you plug in infinity into here because that's what we're doing, t approaches infinity. Natural log of infinity is just infinity. Remember, natural log doesn't actually have a horizontal asymptote, even though it does seem like it's, it doesn't seem like it's increasing, but it is increasing forever and ever and ever and ever in that direction up there. So for sure, this is infinity. You subtract any value, it doesn't even matter. Infinity takes any value that you subtract or add. It's just infinity, so it diverges. Diverges because the integral, by the integral test, the series is going to diverge. Your integral diverges, so the series diverges.